I'm very pleased to be able to introduce colleague and friend John Rundle. John is an external professor at SFI and professor at UC Davis, and as you'll see, John will provide far more than an able stand-in. He's going to be talking about a web-based approach to global risk management. John, welcome. Thank you.
Thanks, Chris. So you may be wondering why you're watching this little movie. If you look down here on the right, you'll see that this movie was actually taken 4 days before the 1906 earthquake. And it was a camera mounted on the front of a cable car moving down Market Street. You can see the ferry building there. You get a sense from looking at this that the city was a very vibrant place. It had citizens who had no clue what was about to happen to them a week later, or 4 days later. And it's really a rather interesting study in our perceptions of disasters. About a week later, it looked like this. The city was destroyed by the earthquake and the fire. We've seen scenes like this in recent times, both in places like Sumatra, Japan, and now and Katrina, New Orleans, and now New York City. I was looking at the Breezy Point photos on MSNBC website last night, and they look for all the world like the Arahama area in Japan and the Sendai area that I saw about a month ago. So we're confronted with these kinds of disasters over and over again, and how can we learn from them, and how can we approach a better sense of resilience from these risks that we face? So that's the question. We have a set of new tools, basically online tools, that may prove useful in the future. And so we've decided, a group of us have decided to explore these. Now, I'm standing here with a man named Shigeo Suzuki. This was when I was in Sendai, and we're actually standing on the remains, or what was left, of his town. This was a fishing village northeast of Sendai. He has lived here all of his life. In fact, he survived the 1960 Chilean earthquake, a magnitude 9.5 earthquake that caused a 4-meter tsunami in Japan. This particular tsunami was 20 meters at this location. There were approximately 600 houses in this location, and all but 2 of them were wiped off the face of the earth. This was the tsunami. I didn't actually realize where this was taken until I flew in there. You can see the Sendai Airport runway here at the bottom right. This is the train that takes you from Sendai into the airport. And this is probably about a half an hour after the earthquake or so. This is a view of Takanura looking towards the inlet where the village is situated. Tsunamis actually travel across the ocean at about the speed of a jetliner, and they're roughly a half-meter high when they do. When they reach shore, however, the speed slows down because the speed is inversely proportional to the depth of the water. And there's a plug of water about 20 miles long behind it, and that the farther end catches up to the nearer end, the tsunami builds up, and you get the 10, 20-meter heights that we know about. This particular area is kind of interesting because all along the northeast coast of Japan now, the coast is about 2 meters lower than it was before the earthquake. I should point out that the last earthquake of this type was in 869 AD. It was the Jogan earthquake, and it created a bigger tsunami than this one. This is kind of interesting because this dock is now a half-meter underwater, and it was a bit of a surreal experience to stand there and walk on a dock that used to be about 1.5 meters or 2 meters above sea level, and now it's a half-meter below. And it will stay a half-meter below for many decades, and over the next 1,000 years, the earthquake cycle will gradually raise this area up above sea level again, and then presumably it will repeat. I actually discovered a photo of Mr. Suzuki in the National, which is the United Arab Emirates English language newspaper. This actually is a very interesting dilemma that they have because, as you might be aware, you might say, who in the world would live on a coastline like this that could be subjected to tsunamis? Well, in some sense, you don't really have a choice. You can't abandon coastlines. They're too economically important. We see that in New York in the discussion to build seawalls around New York. We see that in New Orleans, and we see that in Japan. Moreover, you can't really relocate the village because someone in Japan owns all of the land, and so you can't just, do eminent domain and take the land over. So there's a question about what you do, however, how you can create a more resilient society in places like this. This was the most overwhelming image that I got. This is the Arahama Plain. About half the grave markers in this graveyard are new. And as you travel around northern Japan, you see many, many cemeteries, and the grave markers are all new for the most part. The black ones are the new ones. So it's a sense that you get a sense that the human cost to these things is just staggering. This is a map of natural loss events in 2011, or halfway through 2011. It included, for example, the New Zealand earthquake, the Darfield earthquake, and the Canterbury earthquakes, the tsunami, and so forth. And from this, you get a sense of looking at the map like this. This came from Munich Re. You get a sense that disasters happen everywhere and to everybody. And in the West, or in the developed world, I should say, in the developed world, we typically spend quite a lot recovering from disasters. In the developing world, the loss of life is tremendous, but the actual economic damage is low. And you see that in places like Haiti, where there was a tremendous loss of life, about 250,000 people, but the economic cost of it was, I say, only $10 or $12 billion. Whereas in places like Japan, the loss of life was much lower. It was about 20,000, but the economic cost is probably on the order of $200 to $300 billion. I won't have much to say about this in this talk, but oftentimes when I give this talk, I show this slide, which was a New York Times article. It's recently been realized that many of these disasters share a great deal of similarities with the financial markets. All of them have, or both of them have, fat-tailed statistics. We discussed this at some length on Thursday in the Risk Working Group meeting. And the interesting part about these fat-tailed statistics is that you have finite means but infinite standard deviation. So they're very different animals than what insurance companies are used to working with, which are typically more like Gaussian distributions, which have finite means and finite standard deviations. So what this means is that the whole notion of insuring against these kind of disasters is very difficult because in principle, sometime in the future, you could have a huge event that is very difficult to plan for. Well, we talk about the four phases of a disaster being anticipation, mitigation, response, and recovery. The anticipation phase is really related to forecasting. How well can we forecast these events? And that's a problem. We'd like to be able to forecast these with some accuracy. However, there can be occasionally political difficulties. You've probably heard about the situation in Italy where 7 scientists have been indicted and convicted for, in the popular thinking, failing to predict the earthquake. That's actually not true. They were indicted for and convicted for failing to communicate adequately the risk. I've recently seen some articles discussing Italian law. Italian law is quirky. It's not like English common law, so it has the notion in there that you can be liable for things which you really had no control over if you did not take adequate steps to ameliorate the problem. In fact, I guess Italy has had issues of persecuting scientists since at least the time of Galileo, so it's not really clear how how much this is peculiar to Italy and how much it may have implications elsewhere. So anticipation is there are various time scales involved in this. The anticipation phase you can think of as being years to decades in length. The mitigation phase is typically the engineering phase when you want to prepare for disasters by building seawalls or strengthening your homes. That typically happens over a decade or so. The response phase, obviously the event has occurred and the first responders are trying to save people and dig people out of buildings and whatnot. This is like days to weeks. And then there's a recovery phase that's basically economic in character. How do we pay for the reconstruction? In Japan, all of the people receiving government salaries, and I think many others, are taking a 10% pay cut for probably the next 10 years to pay for the cost of recovery from the earthquake and tsunami. Well, I want to discuss with you today a couple of websites. Mainly it'll be this one. the Open Hazards site that we built that's basically free, and you can find many free tools on there, several free tools that can be of help in preparing for these disasters. But I also want to mention the NASA JPL QuakeSim website that we work with a fair amount. This is a resource for researchers, and some of us are basically starting these websites and starting these tools because we became fairly upset with the notion that we spend our lives in the scientific community writing papers and putting them in the literature, and if you're lucky, 100 people will read your paper. If you're really lucky, 1,000 people will read your paper, and maybe if you're unlucky, in fact, most papers, I think this has been documented. It's another fat tail statistic. The average paper has essentially a half a citation when it gets written. So most papers are not read by anyone. So I think people like Mark Newman are much more qualified to talk about that than I am. But the statistics are there. We actually tried to do or want to do something about this by taking some of the science that we've done and really putting it out there for the public and making it available. So we formed this company, openhazards.com, or the Open Hazards Group. Our CEO happens to be a guy named Bill Graves, who was the first CEO of Cisco Systems, which, as you may know, was founded in 1986 by Sandy Lerner and Len Bosak in Silicon Valley. And after about 15 years, it was worth about $500 billion, briefly, before the dot-com crash. So the forecast that we run on this site, and I'll talk about this and some other things as we go along here, it's a pattern recognition method. It uses the Advanced National Seismic System Global Digital Earthquake Catalog, which is there for anyone to look at. And it's based on the idea that there is this fat tail distribution that's been known since 1942 called the Gutenberg-Richter distribution. And loosely speaking, we can say that the Gutenberg-Richter distribution means that for every magnitude 3 earthquake or larger, for every 1,000 magnitude 3 earthquakes or larger, there's one magnitude 6. For every 10,000 magnitude 3s, there's one magnitude 7, and so forth. So this basic fact leads to the following idea, which is that if you've just had a magnitude 6 earthquake, then what you should do is start counting small earthquakes, magnitude 3s, basically. Most of the events will be 3s. When you've reached 1,000 magnitude 3s after the last 6, then it's about time for another magnitude 6. So if you take that simple idea and translate it into a probability, using something like a Weibull probability law, you can generate a forecast, which I will show you. The advantage of this is that it's fully automated. It can be back-tested and optimized. Again, there's the issue of whether past history is an adequate representation of the future. And, of course, we've seen this now with Hurricane Sandy. We've seen it with the Japan earthquake. If you have an event that happens only once every 1,000 years, we don't have any data on that to speak of. The other advantages are this can be updated in real time and various other things. The probabilities, as I'll show you, can actually change rapidly in time. So earthquake probabilities are known now to change rapidly in time for a variety of reasons, and I'll discuss those with you. So this is a plot of a forecast in Japan. It's the chance of an earthquake during the next 4 years of magnitude bigger than 7.25 since 1980 to up to basically today, actually September 15th. And you see here the big earthquakes that have occurred. This was the earthquake and tsunami in Japan here. And so what you get a sense of here is that, remember, we're counting small earthquakes since the last big one. So this earthquake just occurred. So there are very few earthquakes, very few small earthquakes that have occurred immediately after, but they build up over time. And eventually you get to a stage where you build up to the next big earthquake. And so there's a notion of a cycle going on here that you can see. We backtest these for accuracy by several different tests. 2 of these are shown here. This is called a reliability diagram. Behavioral economists, Leibson showed at our Morgan Stanley meeting, showed similar kinds of plots. I've forgotten what he called it, but this basically starts with a Breyer skill score and uses various ideas to construct these. It's a plot of the observed frequency of occurrence of these big events versus the forecast probability. And so ideally, you would like the frequency and the probability to be 1-to-1 in correspondence, and so they ought to lie along this diagonal line. So the fact that this doesn't tells you that the forecast is somewhat inaccurate, but nonetheless, it's not too bad. What we're doing here actually is we're under forecasting the probabilities. This particular diagram is called a receiver operating characteristic diagram. It was originally, these kinds of things were originally developed for detecting radar signals. It's a plot of the success rate as a function of the false alarm rate along the bottom. So a very good forecast would have a high success rate. It would be up here, and a very low false alarm rate. Okay, so these types of plots should, if they were a really good forecast, it would go up here and step over and then go across to there. So the fact that it doesn't do that tells you it's not a perfect forecast. I should point out, however, that in California, there's a group that I've been involved with for 10 years. It's run by the U.S. Geological Survey, called the Working Group on California Probabilities. And this group takes a different approach to forecasting, which we don't particularly like. What it does is to gather people in a room like this and ask them to vote on various aspects of the forecast. So they will vote on what sort of statistics to use. They will vote on which data to use. They will vote on just about everything having to do with the earthquake. And so the problem is, because it's so filled with opinion, expert opinion, that it's impossible really to backtest it. So you can't go back and say, this is what I would have thought 10 years ago. Okay, so the advantage of methods like these, which you can automate and search patterns and whatnot, is that you can, in fact, backtest them and get some sense of how they're doing. Well, when I was in Japan a year ago, I met with John Roos, who was the ambassador to Japan, and I showed him some of these plots. This is the forecast. These are forecasts for the probability of a magnitude 7 event within 4 years from, September 15th. That's wrong. Within 100 miles of these cities, these 8 cities. And the city I was in, Sendai here, apparently has a 30% chance of such an earthquake within the next 4 years. The next equally high is Tokyo and Miyazaki down here to the south. And most of these other areas are lower in their probability. So we can plot things like this now. And we can actually show that, in fact, we can discriminate various areas along in the world where we have higher and lower probabilities. So I would actually like to take you through this a little bit and show you some of how this works. Unfortunately, the internet in this room is pretty lousy. Otherwise, I would do this as a live demo. So one of the tools you can go to is this forecast tool. And this is a forecast for events bigger than 6.5 within 1 year and 50 kilometers. And you can see that the highest probability, in fact, the highest probability on the planet appears to be here in the Fukushima Mito area of Japan. Other areas are down here. This is the Ogasawara Islands. In fact, there was virtually no activity until about 3 or 4 months before the Sendai earthquake up here. And then there was a series of magnitude 7 events down here in this area, which appears to, it suggests that there might have been a trigger for the events in Sendai, farther to the north, 600 kilometers farther to the north. So there is the suggestion from looking at forecast plots like this that one can attribute some kind of causal relationship looking backwards in time to what a series of events that may have led to these great disasters. We have on the site low resolution, high resolution forecasts for Japan. And you can actually, if you look at this carefully, you can actually see change. It's hard to see on this plot, but if you stare at this long enough, you'll see that just in 1 month's time, so this is over basically 1 month, this area has shrunk to some degree. This area has lessened in intensity also. And this one also. So basically what's going on here is as time goes on, the activity is diminishing here, and other places on this plot you can find that it's increasing. In California, we have a similar situation. This was a plot made on September 15th from 1980, chance of an earthquake here in percent from 0 to 100 as a function of time from 1980 up until basically now. And you can see that we are at a higher level of earthquake probability according to this, in California, Nevada, than we have basically ever been in the past 30 years. We've had some pretty big earthquakes, such as the 1992 Landers earthquake, magnitude 7.3 earthquake, which did a reasonable amount of damage. The biggie was 1994, the Northridge earthquake, on February 17th, which caused about $40 billion of damage, about $20 billion in insured losses. And that was the event that many insurance companies, either the smaller ones, some of them went bankrupt, the bigger ones, such as State Farm, wanted to drop their coverage of earthquake damage in California. And the state stepped in and said, well, if you stop offering earthquake coverage, then you can't offer coverage of any other kind of event. So the insurance industry is conflicted about how to deal with these things. As a result of that, the California Earthquake Authority was set up. It's a public-private partnership to insure homeowners as a last resort if they can't get insurance anywhere else. The disadvantage, as I mentioned in a comment yesterday, is that there is a fairly high deductible. It's about 15%. And from the calculations we've done that I'll show you in a bit, if you apply those to your house, you'll find that it's very, very difficult to find a damage to your house that is larger than about 10%, especially for homes that have been constructed in the last 10 to 20 years when the building codes have been upgraded. So there's a very small chance that anyone in California in a well-built house will ever exceed their deductible. So the question is, do you want to pay the $2,000 or $3,000 or even more that it would cost per year for an insurance policy that you probably would never use? And in fact, most people have done that mental calculation in California, and only 12% of the population has earthquake insurance. So one of the consequences of that is that everybody's self-insured up to their 15% deductible at least. And so the next time there's a major earthquake in California, you can expect to see a huge damage bill. And in fact, we are now about 140 years after the 1868 Hayward earthquake on the Hayward Fault in Northern California. That was a magnitude 7 earthquake. It was actually called the San Francisco earthquake until 1906. The recurrence interval we know on that fault is about 170 years. So we're well within with a considerable variation, plus or minus about 30 or 40 years. So we're well within the window of the next magnitude 7 earthquake on the Hayward Fault. And if that name rings a bell, by the way, it's the fault that runs under the Berkeley campus. It splits the stadium. In fact, the part that's running under the stadium is sort of steadily slipping or creeping, and it's actually pulling the stadium apart. They recently did a major retrofit on the stadium, I think probably on the order of $50 million. But it's a problem. I was recently, in fact, a year ago at the Greek Theater there. The Hayward Fault runs just behind the Greek Theater up on the hill between there and the Lawrence Berkeley Laboratory, which, of course, works with radioactive materials. So, and if you've ever been in that area on the Berkeley campus, it's incredibly steep. The campus is built on a landslide slope, which is slowly sliding at the rate of a centimeter a year or so. So there's all kinds of opportunities for impressive damage there, and unfortunately loss of life. It's been estimated, by the way, that the damage for such an earthquake would exceed $300 billion with a total economic loss. So far larger than Sandy. So at some point in the future, those of you in the audience from New York, you're asking us for help right now. We'll be asking you for even more help in the future, so sometime. Anyway, this is a plot of the California 4 cities forecast. I should point out again that we have these tests that we perform. The statistics aren't quite as good as for Japan in this particular case, but they're not bad. It's about, the confidence level is about an 80% confidence level that these numbers are sort of correct, in the right ballpark. This is a plot of various regionalized forecasts, and you can see here that the chance of an earthquake in Southern California is somewhat higher than the chance in Northern California for magnitude 7s within 150 miles of these cities within the next year. Okay, so a 7 is bigger than the 6 that I showed on the last plot. The last major earthquake in this area was actually down here in Baja California. You may remember this. It was the Easter Sunday, April 4th, 2010 earthquake. It was a magnitude 7.2 event. It caused about $300 million of damage. But more importantly, what it did was it lit up all of Southern California with many, many aftershocks, a disproportionately large number of aftershocks, which seems to suggest to a physical scientist that the stress must be fairly high if you're seeing this many anomalous aftershocks. And if the stress is that high, it probably means that the event that we compute these probabilities for is not too far away. So on our website, we also have this forecast, which you can take a look at. There are various radio buttons and so forth along here. Again, I wish I could demonstrate this, but the internet is too bad in this region, or in this room. But the interesting thing is I've been following along, and I write blogs about this on the website. Just in the past month, you can actually see some noticeable difference in these contours. For example, in this area here, it was pretty solid, so it was low, but not too low. And here, the forecast probabilities seem to be diminishing. Again, these are conditional probabilities, so they depend upon the fact that we refer to previous earthquakes in the region. These are for magnitude 5 events within the next year. On the other hand, over here on the eastern side, these contours are actually seeming to fill in. So the probability, you would say, is getting larger over there. And in fact, it's kind of interesting because in this region over here, now I've superposed the faults, the mapped faults in the region. One of the interesting things about that is that this particular branch of the San Andreas Fault down here, which runs from the Salton Sea up to Wrightwood, that hasn't ruptured in the last 500 years, and we know that from geologic data. So it's a very long time since it's ruptured. This is the one that we're most worried about. In fact, there is this California shakeout, which happened about 2 weeks ago. It's a statewide drill where all the school children are supposed to drop and hold on and under their desks and hold on while the hypothesized shaking occurs. This is the scenario for that earthquake. And it's estimated that when this earthquake occurs, it will probably produce several thousand deaths and something north of $300 billion in damage. The only minorly fortunate thing about this is that it's fairly far from the populated centers, which are over here on the LA Basin. On the other hand, the LA Basin is a sedimentary basin. It's got a lot of soft soils, and therefore, like the Mexico City Basin, there will be unfortunate resonances which allow the energy to build up in fairly large waves in some metaphorical sense similar to the tsunami. There are some other examples we can see. This was the earthquake that occurred a week ago in Prince Rupert, near Prince Rupert in Canada, and I was in Maui just getting on a plane when it occurred. That was the one that caused a 70-centimeter tsunami in Maui. It was kind of surreal to be interviewed on national news from my car driving home to Davis. And then they put the KHON news radio show from Honolulu on, and I was listening to a radio broadcast from the place I had just left, and they were anxiously waiting to see what sort of tsunami would arrive. I contacted some folks at the hotel. Some of our people were still at the hotel, and apparently there were tsunami sirens going off, and people were being told to move to high ground. So it was a very strange experience. This was a magnitude 7.7 earthquake, and it was... So basically what you would expect to see from the 7.7 earthquake is you would expect to see aftershocks. And indeed, this forecast indicates that the probability of aftershocks in this region has gone up dramatically. Smaller events has gone up dramatically. And in fact, even up to a day or two ago, it's continued to change and fill in. So it's a very interesting situation there, and I'll show you in a moment why it's interesting. But this area of I should point out that this area of British Columbia is actually one of the plate boundary. It's on the plate boundary, and there's a major fault line called the Queen Charlotte Islands Fault that runs up through this region and has been the source of historic great earthquakes. In fact, it's basically up here that this earthquake occurred. This is what is called Cascadia. This is Seattle and Vancouver here. And there is a section of this plate boundary. This is the Juan de Fuca Plate. Okay, and there is an interesting area here. This is this fault plane here is called a subduction zone, and it's known that there was a major earthquake, a magnitude 9 earthquake, on this part of the subduction zone on January 26th, 1700 AD at 9:30 in the evening. How do we know that? Well, the evidence is there's an accumulated body of evidence for this. One is that there are drowned forests all along the coast. And if you go back and you date the tree rings, basically you find that these trees were killed between the end of the growing season in 1699 AD and the beginning of the growing season in 1700 AD. And you couple that with the fact that there was what was called an orphan tsunami that hit Japan 10 hours later, and it was about 3 to 4 meters high. No one in Japan knew where the tsunami came from until they put 2 and 2 together. it was fairly clear that this earthquake, which is very similar in size to the Japan earthquake, the Sendai earthquake, and to the Sumatra earthquake of 2004, that the recurrence on these things now is known to be about 500 years. And so we're 300 years into this cycle. Again, it's not a precise, the 500-year recurrence interval is not a precise number. It could range anywhere from 300 to 700 years, for example, for these kinds of events. One of the interesting features about this area, it was first discovered in this area, is a phenomenon called episodic tremor and slip. And so if you have a series of GPS, Global Positioning System stations that are set up here in a network, you can see actually that there are a series of creep events that happen, that's the little dips here that happen, every 14 months or so, and that these are accompanied by very small bursts of earthquakes deep down on this fault plane, and these are called episodic tremor and slip events. And we now know that this is an ongoing feature of this area. We don't know if this is we don't yet know if this is an immediate pre-catastrophe series of events or whether this is normal. The interesting thing is that these events here are now being seen in many fault zones around the world. And in fact, even in Parkfield, California, the place where we've had these magnitude 6 earthquakes every 20 years or so, it was seen that following the Sumatra earthquake in 2004, just before the earthquake in, actually it was just after the earthquake in the Parkfield region, it turns out that we saw a burst of this kind of activity. So we don't know if this is normal or if this is anomalous at this point. There's not enough data in the database to tell. But nonetheless, it's certainly rather unnerving to see these kinds of events going on. And we will be very fascinated to see what happens as a result of the Prince Rupert earthquake that happened a week ago. Will these events speed up? Will they get closer together? Or what? Is the Prince Rupert event, is that a precursor to a much larger event here or not? We don't know enough about the physics yet to be able to say. Okay? So it's certainly a concern. The last major earthquake in this area was an magnitude 8 earthquake on the Queen Charlotte Islands Fault in 1949, so it's been quite some time since we've had an event like that. So in terms of this particular website, you can go and you can click this box called the Circle Selection Tool and generate a little dialog box will pop up. You can generate a circle, and if you hit the Create Report button, you can actually get a plot of like this, which is the chance of an earthquake as a function of time into the future. And this gives you some sense of what the probability might be for an event bigger than 5, 6, 7, and 8. So we build tools like this that are available for use. There's an example of a home damage estimator. I was telling Ginny about this the other day because she has a question. She has a house in, or is it Fullerton or somewhere? And the question is, what about earthquake insurance, which apparently would for her cost $1,500. That's not terribly unusual. Usually it's more. So this was a slide I made for a talk I gave in Southern California. There's some house and some faults there. It's surrounded by faults which have been the scene of some magnitude 6-ish events in the not distant past. The Puente Hills fault here is hypothesized to be the source of a future magnitude 7 earthquake directly under downtown Los Angeles. Anyway, you can take this thing, you can put your cursor on this little earthquake icon, put it on some fault, set the magnitude, and you can generate a report like this that tells you that from this earthquake you would expect to see about 28% damage to the structure and an estimated damage of $73,000. So for this house, probably earthquake insurance might be worth it. Okay, so we also can do more complex calculations, and we sell little reports that if you don't feel like going through this process, you can buy those things and estimate it. The other thing that we have decided that we wanted to do is the following. It turns out that in the Sendai earthquake, the Red Cross was able to get information to Ambassador Roos in about 8 hours, 8 to 10 hours, about the folks, the Americans in the region that were at risk. But they actually found out, the ambassador's office actually found out much earlier than that through Twitter and Facebook. So they found out within minutes, tens of minutes, that a variety of Americans were at risk. Fortunately, not too many in that area. And so it's fairly clear that social networking is going to be play a major role in disaster response in the future, and now we've seen that with Sandy as well. Okay, so part of the idea that this website is designed to address is to use social networking together with these tools. So the idea is that originally it sort of started off as a website with some tools. It now looks like it's morphing into a social networking site that has some tools on it, which people can use to inform each other, form local groups, local disaster resource networks. I think this is a very Santa Fe sort of crowd, wisdom of the crowds kind of thing. I think this is the way disaster resilience is going to go in the future. Certainly there is a role for top-down, government-sponsored sets of instructions and priorities. The problem here is, of course, most people tend to ignore them because they seem to be, you get periodic notices from the government that you're supposed to do something. It's probably much more effective if you self-organize, if it's a bottom-up thing rather than a top-down thing. So that's something that entails or makes room for a lot of interesting research and a lot of interesting possible avenues in the future. I personally don't use Facebook too much because I got sort of turned off to it when one of the people I was friends with was always playing that silly Farmville game, and I was hearing that she caught a fox every 5 minutes or something, and I wasn't too interested in that. So we decided we needed something a little more dedicated to this particular thing. So that's why we decided to go in this route. So here's the social networking side of it. It's on the community page. And there's things like galleries, and here's a nice picture of Doug sitting up here. I put this up here just for Doug during the reception phase. And there's some other things. There's some photos of the Japan Sendai situation just after the tsunami started. Here's some of the photos that I took of the Takanura and Sendai area. This is actually Ed Thorpe. This is our Morgan Stanley meeting. It's Ed talking about financial risk, which I found very interesting, and so forth. So I'm actually going to leave it here. The earthquake risk that we compute changes in real time. The earthquake risk in Japan is largest along the northeastern region of Honshu. That's not a big surprise because we'd expect to see essentially aftershocks of the magnitude 9.1 earthquake that occurred. I should point out that in earthquake insurance in California, it makes a difference if the aftershock occurs within 15 days of the main shock or at a time later than that, because if it's within 15 days, then there's only one insurance payout, and if it's outside of 15 days, there are two insurance payouts. I was interested to see that Sandy has a similar situation. It makes a difference whether it's classified as a hurricane when it actually came on shore versus a tropical storm. Because if it's a hurricane, then there's a 5% or so deductible that applies, which for most homes would be in the neighborhood of several tens of thousands of dollars. Whereas if it's a tropical storm, then I believe it's a flat $500 or $1,000 deductible. So the people in New York certainly care about that. In fact, the governors of New York and New Jersey have basically threatened the insurance companies not to try declaring it to be a hurricane. So these kinds of strange political issues often enter into disaster planning and disaster response, and it's something to be aware of. I don't know that there's a solution to that other than some kind of political solution, but these days political solutions seem to be unavailable to us because of a certain political party, in part of a political party in Congress. There is currently at risk, a significant risk of a magnitude 7 earthquake in the California-Nevada region. The real-time earthquake hazard can be computed and displayed in web-based methods, which hopefully is going to allow more planning. This California shakeout has gone global. There are now 20 million people registered for various global shakeouts. So this is kind of spreading virally on the net, and it's quite possible that some of these kinds of web-based methods will accompany that viral spread. That's what we're actually in the process of doing. We're talking to the people that are running those things, and there's a considerable amount of interest in these kinds of web-based platforms to interact with those 20, 40, 50 million people that will be practicing drills. So we find that these earthquake probabilities change in real time. That's not a surprise because we know about aftershocks and they happen in real time. We also believe that social networking can enable new modes of disaster resource networks to form your neighborhood network, your local network, your school network, whatever it might be. Again, these social networking approaches seem to have been particularly effective in places like Sendai, and it'll remain to be seen if that's also true of the Hurricane Sandy case as well. So let's have some discussion about this. there's lots to discuss. I think Chris and I were talking about how this whole notion of fat tail statistics really factors into new ways to think about insurance, because again, insurance companies are used to dealing with Gaussian or normal distributions with finite means and standard deviations where risk is pretty predictable, unlike these new situations that we're in, including the financial situation where we have these fat tail statistics where changes of any size can essentially occur.
So first, let's thank John.
Thank you, John. This is fascinating information. I'm sorry. Excuse. Thank you for the information. Probably more or less welcome than for people in California. Question is, earthquakes are finite discrete events. How could you imagine the application of this to slower moving events like drought, water-related problems?
Yeah, we actually have information on flood zones, FEMA flood zones on the site. We actually do run, we're in the process of building up to running a hurricane app that you could download on your cell phone to get information about the wind speeds 6 hours from now at your house. We actually do have a hurricane forecast. I was telling Chris earlier, we had an unfortunate situation where the method that we use is a real-time method. You can run it on a laptop, so we don't actually solve the Navier-Stokes equations like the National Weather Service does. So we have to use input from the NWS, and the particular method we were using was forecasting 5 days in advance that Sandy would just move up the East Coast, which is clearly wrong. So we actually pulled that off the website on Sunday morning prior to Sandy, but we know how to fix it, and so probably next year at this time we'll have some kind of hurricane information live on the website. And so there's that. There's other types of disasters like droughts and wildfires. A lot of this data is available on the web, and it's a question of putting it together and just displaying it. And basically people haven't done that. I mean, Google has made an attempt at doing that with various resource maps. There was a Sandy resource map that I saw that Google had put up prior to the hurricane. Those kinds of things can be done, but I think bringing it all together in one site, integrating it with a social networking, offers many opportunities for disaster resilience that don't currently exist.
Thank you very much, and thank you for a fascinating presentation. I actually had two questions. One, hopefully very simple. On the map you showed of Japan with the various percentage probabilities of a magnitude 7 or greater quake associated with the islands. How do you measure, or from what point do you measure that 7? And I asked in the context of when we speak, we say Japan had a 7.2 Richter scale earthquake, and we speak of the entirety of Japan, but clearly there's got to be a distance relationship to the epicenter for those predictions, and just curious what that is.
Right. Well, without going into a whole lot of mathematical details about it, what it does is if you're sitting on a site, and this is actually something Bill Graves, our CEO, turns out to be an expert in speeding up calculations. Our initial attempt at this took about 3 months to do one of these calculations, and he sped it up so that with some techniques so that it actually computes the world every night in about 11 minutes. But basically what it does is it sits on one particular spot and it grows a circle out to find the last half dozen magnitude 7 earthquakes that occurred. It then fits basically the forecast of those 7 earthquakes. It then allocates a portion of that probability to that site. And it actually also takes into account events in a diminishing fashion that occur outside of that. So the paper on that describes how those regional curves are computed has been published in Physical Review E, and we're in the process of writing up the method for publication in other journals as well.
And then thank you for allowing me a second quick question. Everybody's probably aware of the recent circumstance in Italy where I think 6 seismologists were convicted of a failure to adequately warn a populace of an impending quake. Your thoughts and comments on that? That's a first instance in the world that I'm aware of.
Well, as I mentioned earlier, I think it's partly Italy. They have a funny legal system there that's not based on English common law and individual property rights and individual rights that we have here. But in addition to that, I've been interviewed and I've read many accounts of that action, obviously, in the past couple of 3 weeks. And there was a failure to communicate the level of the risk. They were asked about it. They said, the history is that there was a technician that worked at INGV Rome named Giampaolo Giancani, who worked with radon in volcanic areas. And he saw some radon anomalies in this region, which was known to be seismically active. And so what he did was he put a loudspeaker on his car and drove through these regions broadcasting an alert that there's going to be an earthquake. And, you know, his estimate was that it was going to be 100 miles away from where it actually occurred. He was actually arrested and charged with disturbing the peace. And then a few days later, this commission met in L'Aquila, 7 scientists on this official government commission, and they were asked to comment on the likelihood of this earthquake and whether this guy's prediction was correct or not, because there had been a series of small earthquakes. And basically what they said was that there have been historically small earthquakes, and occasionally there have been large earthquakes in the region, but that it was unlikely, quote unquote, that there would be a major earthquake in the near future. And then outside the meeting room during the break, some reporters asked this one commission member, who was not a scientist, what his opinion was, and he said, and I would like to quote it, I can't quite remember the quote, that you should all go home and have a bottle of wine and not worry about it. And then in a day or two later, the earthquake occurred and 300 people were killed. And when asked later, some of the people that brought the lawsuit, the plaintiffs that brought the lawsuit, actually said that had they been adequately instructed that the risk was higher, they would have gone out and slept in their cars like historically they had done, or stayed outside for several weeks or whatever it took. So, you know, you can make an argument that there was some cavalier sort of attitude about it on the part of the commission. Whether that's, you know, liable for criminal prosecution is another issue, and that has to do with the Italian situation. You know, I don't think that would happen here unless there were some really egregious situation. I guess the Army Corps of Engineers was sued after Katrina, and I think the suit was thrown out of court, I believe. The U.S. government has sovereign immunity, in theory. But occasionally the government does lose lawsuits. There was a case of a NOAA situation about 20 years ago where they actually lost a lawsuit. But, you know, the legal implications of disasters are obviously something for lawyers to worry about.
You mentioned this relationship statistically between the small earthquakes and the big ones. Could you talk a little bit about the physical mechanisms that might be involved? And also, wouldn't one suspect that it's geographically local so that it would vary from one place to another?
Well, it turns out it's rather remarkable. This thing called the Gutenberg-Richter magnitude-frequency relation has been known since 1942. And in Japan, it was actually called the Ishimoto-Aida relation in the 30s when they discovered it. But for whatever reason, we call it the Gutenberg-Richter relation. Usually we don't express it in its actual power law form. We express it as an exponential function in which the coefficient that multiplies the magnitude in the law turns out to be this thing called the B value. So if you were to plot the log of the frequency of events versus the magnitude, it turns out it's a straight line on a plot like that, and the slope is called the B value. Remarkably enough, the B value is almost always 1 everywhere in the world. There are certain situations like volcanic regions which have lots of small earthquakes with no big earthquakes where the B value is large. But the B value can typically vary in a given region from about 0.85 to about 1.15, but very closely around 1. Various people have tried to correlate changes in this B value with the occurrence of a future major earthquake, with not a whole lot of success, just looking at that one parameter. So where does it come from? We've actually done a lot of work. A lot of people have done a lot of work on this over the past 20 years or so, particularly with the advent of ideas like self-organized criticality that Per Bach used to promote vigorously. But basically, we think earthquakes now are a kind of phase transition. If you look mathematically at it, we've actually been able to identify the or write down what we call free energy functions or functionals that look very much like the free energy functions that magnetic systems undergo or illustrate magnetic systems undergoing phase transitions. So the scaling exponents are the same, basically the same as mean field percolation, various other things. So we're pretty sure now that earthquakes mathematically are essentially identical to the kind of phase transitions that you might be familiar with, liquid gas, magnetic, other kinds of things. So that's basically where the scaling comes from.
We have a question from the Phil Moyer, who's watching on the web. Hi, Phil. Hope you're well. The question is related to this last one, and it has to do with the idea that large earthquakes at one spot on a plate can, quotes, trigger large earthquakes elsewhere. Is that myth or is that real?
It's not myth. It's real. By the way, hi, Phil. Good to see you, or hear you, or something. You're here virtually anyway. Yeah, so it's not myth. I mean, you can actually do some calculations that allow you to compute the stress change at another location due to the earthquake. And actually, there's been a lot of work done. There's actually an app that you can download from the USGS called Coulomb that actually allows you to compute the stress changes at various locations around a major earthquake. And there's a very strong correlation with where the aftershocks occur and where the stress change has gone up. So in an earthquake, basically on the fault plane itself, the stress is relieved for the most part, but what it does is that some of that stress just goes away in the form of elastic waves and heat, and some of it sticks around and gets transferred to other areas of the Earth's crust. In those areas, the stress will go up, basically. In some areas, it can go down. So in the areas where it goes up, you actually see a lot of aftershocks. There's a remarkable series of earthquakes along the Anatolian Fault, the northern Anatolian Fault, that occurred starting in about 1935, about 5 magnitude 7 earthquakes that marched down this fault. And basically what people have done, Ross Stein and colleagues at the USGS have looked at this, and they've actually calculated the stress changes from each of these successive earthquakes. And the next one occurred in a region where the stress was increased from the last earthquake. So, but then it stopped. Okay, so it's not so clear why it stopped. But nonetheless, there is a growing body of evidence that says that indeed earthquakes can trigger other earthquakes.
Two quick questions. One quick, one maybe not so quick. On your map for Southern California, it didn't look like you had much elevated risk, some elevated risk, but not that high for a repeat of the Fort Tejon event where the bend in the San Andreas occurs. The second question is, do you have enough data for your method to work in an area like New Madrid, where the seismicity is less?
Well, it's a global forecast. So first of all, so I'll answer your second question first. It's a global forecast, and so you can go anywhere and get the same kind of information. But we're limited by the quality of the data. In various parts of the world, the ANSS catalog is pretty lousy. In most of the U.S., it's pretty good. In California, it's the best anywhere. So we can see earthquakes in California, and they're in the catalog down to magnitude 1, even 0. In places like the East Coast and central U.S., it's probably good down to magnitude 3, going back about 30 years. So it varies from region to region, but we certainly can look at the mid-continent area. For your other one, other question about the Fort Tejon area, it's certainly true that the probability is somewhat lower there, but you have to remember that we're dealing with probabilities here, and so nature rolls the dice. We can compute the probabilities and the odds, but nature's going to wind up rolling the dice, and you do expect a certain fraction of events to occur in low probability areas. It's been 160 years or so since the 1857 Fort Tejon earthquake, the last big one in Southern California. Lisa Grant, our colleague at Irvine, UC Irvine, has recently gone out and dated events in the Carrizo Plain area, and she's found, contrary to what was thought before, that events tend to have recurrence, average, quote-unquote, recurrence intervals of about 140 years. And these are 4-meter, 5-meter slip events. They'd be a magnitude 7.5 earthquake. So we have reached that recurrence time now in the Carrizo Plain area, and so there's a reasonable expectation of an event in the next decade in Southern California that would do serious damage to your hometown.
John, I came a little late, and I
Yes,
hope
I
you
noticed.
Yeah.
You can't sneak in.
So I hope you can forgive me if I ask something that you already touched on at the very beginning, and I should wait till afterwards, but I'm really dying to know the answer, and I can't wait. So how much of your forecasting depends on having a model of what's actually happening underneath the world and the plates moving and things interacting and shocks being distributed, and how much of it is a statistical projection based on observing things and noticing in the past that these kinds of things that happen tend to be correlated with future events that happen and things like that. And I guess if you've already answered that, to make it a slightly subtler question, in general, do you think this kind of forecasting could evolve from the physical modeling to the statistical, or do you always think that in the end you have to have the physical modeling to be successful?
I'm glad you asked me that question. One thing I can do here is to show you the answer in part. So the simple answer is that the method that I showed is statistical. Basically purely statistical. So it's looking for patterns in data. This is another kind of model that we do. This is exactly the type that you just referred to. It's a model of, you set up the faults. These are all the known major faults in California. We input all kinds of geological data about the average slip rate on these faults. We have friction laws that describe the way the earthquakes actually occur. And so we can do these simulations like this, which we can run these for millions of years to create synthetic earthquakes and then look at the statistics of those simulations. There's, of course, an issue of taking these things and tuning them so that they represent the real data set. There's other kinds of simulations that we do, like this one, which builds upon the one I just showed you. These little butterfly things are what are called INSAR interferograms. So you have these major earthquakes that occur every so often, and some of them are shown with these butterflies. This is what a radar satellite would see flying overhead using these techniques of radar interferometry. If we let this thing go long enough, and I'll let it go long enough, there's a magnitude 8 earthquake in here that looks like it splits California in half about 2/3 of the way through. So we'll sort of leave that up there until we see that happen. But anyway, the simple answer to your question is what I've showed in the talk is statistical in nature, and it's sort of generally applicable. But we also build these models, and the USGS has got a project to use these kind of things in improving their forecasts. I'm somewhat dubious about the utility of these because the amount of data we have is extremely small in relation to the number of parameters in a model like this, which numbers in the thousands. So there was the event. Nothing like this has happened in California that we know of, by the way, where the north and the southern section went together, but there's actually nothing to prevent it from happening physically.
You don't foresee in the future then the modeling approach, being practical?
It depends on what you mean by practical. Given the fact that we're sort of starting from a very low level, it's certainly informative about directions we can look at. We can also try our same statistical methods on these kinds of things, which are more physics-based simulators, to see how well we do. It's kind of like the difference between having an econometric model, I guess, with all the feedback loops and the Federal Reserve doing its thing and whatnot, and versus a statistical quant-based approach to forecasting markets. So actually, I haven't pointed it out, but in the Morgan Stanley meeting, I mentioned that we actually have a fund that we're running. We took some of these methods and morphed them into financial forecasts, and so we're doing some fun experiments with seeing how our fund behaves. And currently, we're up pretty well. As of last night, we were up 10.5%, 11% year to date, which is far better than the average hedge fund. So.
Can you link a time and a date, expected time and date, to when it's going to happen? So.
All we can do is forecast. We make a distinction between forecasting and prediction. Forecasting is the computation in our vocabulary of probabilities. We cannot specify events. We don't have the data or the knowledge to be able to specify the occurrence of an event. We can't tell you that a magnitude 7 earthquake will occur next Tuesday in LA. Can't do that. Wish we could do that, but we can't do that. All we can do is say there's a 17% probability of a magnitude 7 within 150 miles within the next year.
Thank you, John. I have a question about. I should first mention, in climate prediction, the statistical models, for example, of El Nino prediction, do exactly as well as the mechanistic models for El Nino prediction. So there hasn't seemed to be, in a completely other area, any change in skill between the statistical approach versus the mechanistic approach. I'm curious about what happened a few years ago at the geysers and all of the geothermal activity that was creating microseismic earthquakes and the potential risk of human activities, whether it's in oil or gas extraction or geothermal efforts or potentially CO2 sequestration and seismic risk. And I was wondering if you can use your statistical method to look for outliers that are substantially more seismic than what you would predict based on the data. Is that something you've thought about?
Well, actually, we've certainly thought about it. Bill Ellsworth of the USGS has actually given a paper on that at the SSA meeting last year. It turns out that fluid injection is now known to cause earthquakes. And it started with the geysers. People began to understand it then. There was the Rocky Mountain Arsenal in Colorado, which produced a magnitude, I think it was a magnitude 5.9 earthquake after a few months of fluid injection. And then, of course, we have all this evidence now that's being acquired from the fracking operations that we see all around. It turns out it's probably not the fracking per se that causes the earthquakes. Yeah. It's the re-injection of the fluids. There was some slight suggestion that maybe the mineral earthquake that affected Washington might have been related to something in West Virginia, but I think that's been pretty widely debunked. It's certainly true that there are many more earthquakes, about a factor of 50% more small earthquakes in Oklahoma and Ohio than there were before fracking operations began several years ago. So there is certainly evidence for human production of earthquakes. And the interesting part is, in general, you do have this Gutenberg-Richter relation, which says that for some number of small earthquakes, you'll get a bigger earthquake. And as far as I know, that law is generally valid. So, if we're producing many, many small earthquakes in a region and we get up to a very large number, it could be followed by successively larger and larger earthquakes. So you could see, as a result of the injection operations, unexpectedly large earthquakes in many parts of the U.S. I actually got a call from a guy in Armenia, the president of the American University in Armenia, who's a friend, who was worried because the U.S. has signed a memorandum of understanding with Armenia to promote fracking operations in Armenia. You may remember the Spitak earthquake, which caused about 20,000 deaths a couple of decades ago, 3 decades ago. And so, to the extent that people are starting to do this in known seismically active areas, it does increase the risk of major earthquakes, major activity. Between Armenia and the U.S. Yeah.
Other questions? Please try and one last, Bob. Go ahead.
Yeah, coming back to the social networking. For social networking after disaster, what you want to do is find the one site that's the right one to go to. Mm-hmm. What mechanisms do we have for causing that? Because most people aren't going to know ahead of time that, for instance, you set up this site, and in particular, people want something that's really local. Mm-hmm. So how do we find those things?
It's a good question. I don't know the answer to that, but it's certainly a very relevant question. The thing I worry about is all the cell towers going down after the earthquake, and then you don't get any information.